Hey everybody, let's do a what do you call makeup class for the class we missed. But yeah, this one's gonna be short and it's gonna be pretty useful actually. It's a statistical test for civil engineers, or yeah, for dummies. Yeah, you like the for dummies books? They're pretty good. But so here, I mean seriously, I'm gonna practically tell you the minimum you need to know to do statistical testing. We did I asked you on last class, anybody used that before or familiar with it? People heard of it and then they kind of know what it does, but there's actually a lot of study on this. And then you can go really deep into this. Statisticians do that. And then other scientific fields like biology, medical, they do those type of things, and social studies. They do those type of things. It's like their bread and butter, their living blood. But for civil engineers, I mean, typically we don't have that many data as the biotechnical or medicine, and then our regulation is not like FDA. Our regulation is more empirical, so we typically don't need to do this very often. But it's always good if you want to make a strong argument. So here we go. What is it? Statistical testing, it's just a group of procedure you will follow to make a judgment about some data you have. For example, someone ships you some concrete and then they claim this is a 5 KSI concrete. You want to make sure that it is at least 5 KSI, right? So you will do some cylinder test. Here you can follow some standard procedure, ASTM for concrete strength testing. They say you take I don't know, yeah, don't quote me on this, but yeah, say if you take like 5 samples, like 3 has to pass or whatever. But if you don't have those, like what do you make a decision? So you do maybe not 5, maybe you do 10 tests. And then you look at the data, and then how do you know it is 5 KSI? Or because you're gonna have some tests that's greater than 5, some are lower than 5, and then what do? You say, okay, well, out of 10, I want everything above 5. That seems a little bit like harsh. Okay, so then you say, okay, how do I draw the balance? Like 1 not pass, 9 passes, still seems to be harsh. So statistical testing is like a very fair judge based on statistical derivation. That there's a standard procedure you go through, and then you select a significance level. Yeah, you have to do that. Then you can view as the probability of your judgment is wrong. So basically, your claim is wrong. Your claim the average is 5, or average is greater than 5 KSI. So go through the procedure. If you say, okay, the significance level I want to do, they typically call it like some people call it p-value, some people call it alpha value. You say if I select 5%, which means if you follow the procedure and came out to a judgment, and then you make that judgment, then there's only like 5% chance that your judgment is wrong. Or sometimes you want to be like truly very, very exclusive. You see 1%. Also keep in mind everything probabilistic. This testing, although it will support or help you to reject a judgment, it's not always 100% right. It's not a golden pass, okay? First of all, I've seen people using statistical testing and then they apply it with like 3 samples. Nobody preventing you from doing that, but you have to be an engineer first, okay? We're not statisticians. I think like using 3 samples to do it, statistically you're right. I mean, the procedure would be fair because it take into account how many samples you have. But yeah, so you want to be reasonable. So that's a beginning. Secondly, how does we do it? All statistical testing, doesn't matter what you are testing, they actually follow a pretty standard procedure. Yeah, let me kind of enlarge this a little bit so that you can see. Oh boy. Yeah, that doesn't help. Hold on. Yeah, let me just do this. So basically, the first step of every statistical testing, you have to have a what they call null hypothesis, and then which is always a statement of equal or is. This is quite important because sometimes people are thinking, oh, can my null hypothesis be like my average is greater than this? No, it cannot. It has to be equal or is. For example, it's like my sample mean, like the mean value of my concrete is equal to 5 KSI. Or the first batch and the second batch, their means are equal. Then you're like, okay, why does that always have to be like equal? Yeah, there's a reason we're going to talk about later. And you'll see why the reason there is. Then, after choosing your null hypothesis, you can have an alternative hypothesis. You can have a couple choices here. It can simply be not this. So when you say it's equal, you just say not equal. When you say like the batch 1, batch 2 are different, are identical, has the same means, you can say they don't. They're just different. If that's your alternative hypothesis, that means you are doing a two-sided test. Which means like you are looking at if they're going to be either smaller or bigger, then you can reject your null hypothesis. Or alternative hypothesis can be my concrete strength is greater than or equal to 5 KSI, or is it smaller than? When you do that, you are doing a one-side test. So those are your choices, typical choices. Either do a one-sided or do a two-sided. If you do two-sided, you only get the judgment that they are either equal or not equal. But if you do one-sided, you can get more information. So people can think of this as kind of more powerful way to do it, but we'll talk about that later. You don't always need to do either one of them. And then there's engineering judgment in choosing which one to do. So once you defined your null hypothesis and alternative hypothesis, you can calculate a statistic value from your data. So say you have 3 data points or 10 data points, there will be a formula in this test, whatever test you are doing, that tells you how to calculate statistics from that data. Then you get a value, right? Then the test itself will give you a presumed statistical distribution of this value. You're like, how did they do that? They do that by assuming your null hypothesis is correct. So basically, they'll say, if the mean equal to 5, if batch 1, batch 2, their means are equal, then if you go through this calculation, the result you're gonna get will be for sure, if they are equal, for sure following this distribution. This actually highlights why your null hypothesis has to be equal or is, because this is almost like a what is called a boundary condition or a known condition, so that you can actually derive this distribution. right? This distribution has nothing to do with your data. This distribution is determined by your null hypothesis, which when they derive it, they assume it is the truth. Then the way the statistics are calculated. So basically, it's like we covered early in this class. It's the distribution of a function of random variables. So they do that purely by your null hypothesis. Now, here's the funny part, right? You have a assumed distribution, then you got a value actually calculated from your data. So you see where your actually calculated value from the data will fall when compared to this distribution. If your sample calculated statistic falls in the what they call rejection zone, then it is highly unlikely your null hypothesis is right, because I mean your distributions think most of your data is going to be in this region, but your sample calculated is in a region in the tail. So it is very likely your null hypothesis is not right. Then you have no choice but to reject it and then believe in the alternative hypothesis, which is either this guy, they're not equal, or they can be greater or smaller than. Once you do that, you can then make a decision based on that. So at the end of this, you either accept or reject your null hypothesis. And then if you reject it, depending on what your alternative hypothesis is, you can make some other conclusions. The rejection zone, this guy is depending on the significance level. If your significance level is, I don't know how to say it, it's high or low. Yeah, basically you want your result to be like very significant. Then your zone's gonna be bigger or smaller. And also, if you're doing one or two-sided test, your rejection zone gonna be different. Of course, this makes absolutely no sense unless we do some examples. So let's but let's kind of illustrate that with a drawing board, paint, like we always do. So say you have you have a null hypothesis like H0. Typically do that is my concrete strength from this batch of concrete is equals to 5 KSI. Okay. Then let's first do an example with the alternative that is the two-sided, which is like mu is not equals to 5. So what you do is that say you have a whole bunch of samples. Yeah, let's do it in red. 1, 2, 3, 4. Okay. Maybe you have more than 4. Maybe 5, 6. Yeah, 6 of them. Then you test them. They came in different numbers. Say this one's 4, this one's like 3, this one's 7, this one's 5, and I got another 5. Yeah, of course, this is just hypothesis. Yeah, look at this. I mean, like, what do you do here? So you say, okay, I'm gonna do a test. Then the first thing is like, what kind of test do you do? If you want to test the mean, it is a student t-test. So you do the t-test, but you're like, okay, how am I gonna do the t-test? So the t-test, you're gonna have this PowerPoint, so don't worry, no need to copy this down. But like for example, you test your mean against a given mean number, right? So you can actually just follow this link. Let's take a look. There's a lot of online resources on this, but I found this one to be very, very accurate and precise from the nest. So basically, yeah, you don't need to worry about that. You see the t-test. Basically, you have this, and then test statistics. That's like the formula you calculate that statistics. We call it the t-statistics. So what you do is you your mu 0, which is the mu you know, is in this case. Oh, come on, let's do this. Is 5, right? So then you got a whole bunch of data, like here. Okay. And then you want to calculate the t-statistic, which is, you just follow the formula. There's not much to it. You calculate the y bar, which is the average of your sample. Okay, you just calculate average of those guys. And then the n is, apparently now you have 6 numbers. It's 6. S is defined above. What is it? S is the sample standard deviation. Yeah, we already know. Yeah, you can calculate that. It's easy. It's basically you calculate standard deviation of those 6 numbers. Then you can kind of come up with t statistics. So yeah, in fact, let's assume. Yeah, you can actually do this in your head. But let's assume the t from those guys based on that formula we just showed you. I don't know what it is. Maybe let's say it's like a 5 point. Yeah, you can calculate it. I didn't, but 5.5, something like that. Okay, so that's you got your sample statistics, and then now there will be a in a kind of a before the computer age where Matlab doesn't exist. Everybody is relying on the tables. You will get a t-statistics table where it will give you the distribution of t as a function of n. Okay, so let's say it looks like this. Let's say let me just draw it with this. Let's say if this is correct. Oh, come on, what I'm doing? Okay, if this is correct, then the mathematicians, they can derive the distribution of t. It's something like this, and then it'll probably be centered about 5, and then it'll kind of spread out. And in fact, I can tell you, if the number of your samples increase, this thing gonna get narrower and narrower and narrower. But anyway, that's not the point here. The point here is that, okay, so now what do you do with it? So now you need to select a confidence level. We'll select 5%. So basically, you just say, I'm gonna either accept or reject this hypothesis, and I'm gonna make sure 95% of the time I'm right. How do you do that? What you do is you just if the alternative hypothesis is not equal to 5, so you're saying, okay, basically I'm gonna cut those off. In those regions, in this region you have a probability of 2.5%, and then in this region you have another 2.5%. What it means that is if this guy is right, and then your sample are really coming from a distribution where mu is 5, it is only 2.5% of chance that it is in this region, 2.5% chance it's in this region. So now let's see what how this guy does, where it falls. So if it falls within, let's say if it falls in here, you're gonna say, you know what? It is likely I'm gonna reject it because those are called rejection zone. rejection zone. If your sample statistics come into those zones, you're gonna reject your H naught. So you're gonna accept this. Yeah, but if it's like within here, then you cannot reject your null hypothesis. So there's a very good chance, actually in this case 95%, that they are really from a mu equal to 5. So this is two-sided. Two-sided is not that exciting, right? Because you're saying, okay, well, it's not equal to, but like, you know what? Look at this. I think it's not just it's probably greater than 5. Hey, look at this. I mean, there's 4 of them. I mean, there's 2 as 5, but this guy looks pretty good. So then you do a one-sided test where you do this. Then you cross out this hypothesis. You say I'm gonna yeah, I'm feeling pretty lucky here. I'm just say this batch of concrete it's actually greater than 5, greater or equals to, or so how do you do that? Everything actually will stay exactly the same. You still calculate those exactly the same. You still have this. The only difference is now, let's do it in a different corner. Your rejection zone changes. So now, instead of doing it on both sides, you just say, okay, if I'm gonna reject this, I'm gonna put the 5% all in here. Here's 5%. Nothing in there, okay? So what I want to do is this is the rejection zone. What I want to do is like now I see where my 5.5 is. If it is within here, then I cannot reject my assumption. So I kind of failed in my purpose. Yeah, I cannot reject it is actually equal to 5. But if this guy happens to be like located in here, then I can actually reject H naught. A lot of people, when they hear reject, they think about negative things. They think, oh, I was rejected. Oh, that's so bad. But in this case, you actually want to reject it because you want to prove that your concrete is better, right? So yeah, if just think about it. If this thing is far away from 5, it will land in this zone. Then you can reject H naught. Then you can, accept this guy with 95% of confidence. Wouldn't that be a good thing? Then, because the distribution, like those two guys, they are exactly the same. So you could say there will be a situation, say if my 5.5 is just right here. It could come into a situation where you fail to reject a two-sided test, but succeeded in rejecting in a one-sided test. Because remember, if this is just 2.5, and then this entire thing, this is 5, you got a little bit of leverage here. It can happen, and then it is up to your engineering judgment if you want to believe that or not. But whatever you want to believe or make decision on, you have the statistics backing your judgment. Okay. This is just an example of like a t-test on the mean. There's other tests. They test some test variance, some test that, but it's the same idea. You got sample, you calculate the statistics, then you construct your hypothesis. It's either not equals to, or you got your greater or smaller than. Then you do your test. Then yeah, of course another option is like if you do smaller than, then your rejection region will be here. You reject the null hypothesis. If your thing's landing here, then you know it is significant. It is statistically significant. That's a good chance that your sample mean is smaller than 5. So that's a two-sided and one-sided test. All right, let's come back here. Yeah, I'm gonna send this to you so you can study more. But anyway, that's a good example. The back to like engineer, the minimal you need to know. First thing you need to know a test about the mean. So that's a t-test. It is likely the most useful in civil engineering applications because we worry about means quite a bit. It is actually probably the most popular tests out there because you got a sample or you added some concrete other mixture in your concrete. Then you want to see if the two groups are control group, and then when you added that, if the strength increase or if the water ratio increase or whatever. So there's two types, right? There's what they call one sample type, which is what we just did here. You test your sample against a given number, 5, 6, 10, 1,000. It's a given value. And another one is compare two sets of data, compare their means, like I just said, the control group, and then the test group. Those are the tests you do. They're all t-tests. Then I think we just covered that. Like for the mean, it's easy to imagine you can be doing one or two-sided. Actually, it's a typo. If you do one-sided, it appears that your outcome will be more powerful because you're indicating an effect, either a positive or negative effect, because greater or smaller than. If it's doing two-sided, you just get not equal to. Okay. But you need to know what you're doing. You don't really want to do a one-sided test just to get what you want. Yeah, a common mistake people do is that they really think coming in with prejudice against it. Hello? 我在微信待会儿就给你打。 prejudice against the data. They say, "Oh, I want to prove this." They'll kind of raise their arms to actually do a test and then they pass. Don't do that, okay? Then there are situations, like I said, you can accept H naught for which is null hypothesis for two-sided test, but reject that for one-sided test with the same data and same confidence, same alpha value. We just showed that. And again, rejecting, sometimes when you're doing one-sided test, rejecting H naught is actually what you want to do because H naught is everything's equal, right? You don't get anything. You want to reject it so that you can accept it's greater than or equal to. So there's other test. We said that there's a mean test. There's a variance test. It's less common but can still be useful in civil engineering applications. So, for example, you have better QC on a concrete mix. You didn't change the design of your mix, so the mean of the strength should be the same. You didn't change anything, but you have better QC, quality control. You paid like $100 for a guy to actually look after your workers. After a couple of months, you think, is that $100 worth doing? You can do a test to see if the variance, before and after you have the QC guy, if the variance of your concrete strength decrease, right? If that's smaller than the previous one. Or you can just test your variance against a given value, which is chi-square, another is f-test. Okay, so typically here's now when I'm gonna do a Matlab thing, but you know what? I'm not gonna do that. I'm gonna actually just lead you into it. So those are the 4 functions you can do those tests. And I'm gonna assign a homework, which will come in an email soon. yeah, today actually. Oh yeah, this is the recorded message, so not today but soon. um, where you're gonna try this on some data I give you. I'll have you do some tests, not all of them, but you need to kind of just go to the help. Those are easy. The reason I don't do them is actually they're quite easy. You do them, and then if you have questions, you can always ask me. All right. Thanks a lot. And then this will conclude our like statistical testing for engineers.